Hey everyone. I wanted to create an addendum to today's lecture because I feel like when we ran out of time, there were still some questions about quick selects, and I wanted to hammer out some of the finer details of the algorithm. So let's begin. We have an array of n unsorted elements, right? And so we want to find the element of a particular rank. So the rank of an element is basically what index it would have in a sorted array. So over here, I put down the ranks of the elements as so. And so we want to devise an algorithm that could return to us, say, um, the element at rank 7, which would be 42. Okay, so how will we do this? So the first algorithm is simply to sort the array and return the kth element, where k is the rank we want. Now, this would take O of n log n time because the sorting itself, well, pretty much all our sorting algorithms, the fastest one runs in O of n log n time. The second thing we could do is that we could continuously find the next smallest element in A. So for instance, we could first find the smallest element in A, then remove that element, then repeat this process k times to find the kth smallest element in A. And this would give us a runtime of O to the kn. Now, if k is small, then that's great. We would get O to the 2n or O to the 3n, and that's just O to the n. However, if k is n squared, then we would get O to the, if k is n over 2, I should say, we would get O to the n over 2 times n, which would simply yield a result to O of the n squared. And this really makes sense because effectively what we're doing here is bubble sort. So that's not ideal either. It's not ideal as a general algorithm, I should say. However, it still could be useful if you know that k is always going to be pretty small. But we don't know that. We want to have some freedom in our algorithm, and we want to do better than this, I should say. And so we turn to our option is quick select. And what quick select is, it's effectively an analog of quick sort. We choose a pivot, and then we partition an unsorted array into two parts. One part where the left part, that is, whose elements are less than the pivot, and the right part whose elements are greater than the pivot. And doing so yields two arrays, one who you know has smaller elements than the pivot, one who you know has larger elements than the pivot, but also tells us where the pivot appears exactly in the sorted array. So if the pivot has the same rank as the rank we're looking for, bam, just use that, right? So here's the algorithm. Here's like a pseudocode of the algorithm. And what are we doing here? We're basically choosing a pivot. And so in our case, just this baseline case that we're doing, we're choosing a pivot of A of 1, right? And so we partitioned the algorithm using that same partitioning scheme into two parts. And if the rank of the pivot is equal to k, then we return the pivot. Else, if we return the less than, if the rank of the pivot is less than k, then we recursively perform quick select on this part of the algorithm. If the rank of the pivot is greater than k, meaning we want something in this part of the array, then we recursively do quick select on that part, except, and I should correct this, except that we select the other algorithm and we make sure to decrement um, the uh, the rank we're looking for, because this new array is going to be smaller. So for instance, if we're looking for 7, then when we recursively call, we should be looking for 3. Okay? So this is how this works. So let's look at the recurrence that describes this algorithm. So we have t, and actually let's use a different color. We have t of n, and that is equal to, well, let's look at the individual parts and like sort of fill out the recurrence equation from here. So this choosing the pivot takes O of n time, and partitioning the array takes it takes constant time choosing the pivot, sorry. And partitioning the array takes O of n time, as we know from our quicksort algorithm. And then we either return this array, or we have these two recurrences. So this recurrence is equal to t of, what is this? It's either t of n minus k, I want to say. No, it's t of the rank of the pivot. So the size, the rank of the pivot, or t of over n. Yeah, because we want this proportion of this algorithm, or t of n minus the rank of the pivot divided by n times n. And so these times n's cancel each other out. And actually this would be times n here. So we should be canceling each other out here. Basically, we want this to be equal to the size of the less than array, when this is equal to the size of the greater than array. So we have two options, and we choose the max of these two options because we want the asymptotic bound. Max a that and a that. All right. Plus O of n plus O of 1. So these two, so a constant time disappears to O of n. So we just get plus O of n. Now what's interesting is what happens here. What happens here? So remember that in the actual quicksort algorithm, a lot depended on choosing a good pivot, choosing a pivot that appeared near the center of the array. Now, if we chose a pivot every time that appeared near the center, we would get a recurrence that's basically t to the n over 2, which is equal to t of n. And this would be equal to O of n, simply because the root dominates, and according to our master recurrence analysis, if the root node dominates, then we go with that. However, if we choose a pivot poorly, let's say if the pivot is always at the front here, if we choose a pivot that always appears right here, and we just basically reduce the array n by 1 every single time, then we get a recurrence that looks something like n minus k where k is small plus O of n, which is approximately equal to O of n squared. So not ideal. And so a lot is riding on how we choose a pivot and making sure the pivot appears roughly in the center of the algorithm. And so we got a solution for that. And the solution for that is called the medians of median. The median of the medians, sorry. And so let's look at that real quick. So we got this unsorted array, A, here. Array A has n elements. Okay? And each of these columns represents one mini array. So we split A up into n over 5 element arrays. Okay, and each of these columns represents one of these 5 element arrays. Okay, so what we want to do is find the median of each of these arrays. Okay, and to do that, we don't necessarily have to, but just for the sake of visuals, we're gonna sort them. Now, we don't have to actually sort them in the actual algorithm, but what we do have to do is find the median. For instance, find the median here. We have to find these medians of each of the subarrays, okay? And we could do this in constant time. We could find the median of each of these subarrays in constant time. We could even sort them in constant time, but let's focus on just finding the median of each of these arrays constant time. So now what we want to do is find the median of all these medians. Okay, and in this case, it's going to be 42. And we are going to choose that as our pivot. As pivots. Okay, now, is this a good pivot? And I would say yes. Why? We're done with our algorithm now, so everything that comes after this isn't stuff that we actually do in the algorithm, but I'm going to do a couple things, manipulate this sort of data in ways so that's easier to visualize. So I would say that this pivot is pretty good because if we rearrange the arrays according to their median values, like so, this median of median appears right in the center, which is good. It's exactly where we expect it to be. Now, what we know about this median of medians is that it is larger than all these values here. It has to be larger than the 2 values in its own array because it's a median of its own 5 element array. It has to be larger than half the values of the medians of median array because it is the median of medians. Further, it has to be larger than these values here because since it's larger than this median, and this median has to be larger than these values, therefore this median has to be larger than these values as well, and so on. So what we know is that the median of medians is larger than 3/10 of n, 3/10 of n of the elements. And why is the 3/10 important? Well, if we look at the columns, there are n over 5 columns. And the values that this median of median is larger than it occurs in n over 10 columns because it's n over 5 divided by 2. And then we got multiply that by 3 because it's larger than these 3. So it would be 3/10 n. Okay, and then this 6 And then this -6 comes into play when you do the proof for as n approaches infinity. Yeah, if you want to go through the proof, let me know. But that's just this -6. But the important part is right here, this 3/10 n, which is larger than. You could largely ignore the -6 for most applications. Conversely, using the same logic, you would say this median of medians must be smaller than 7/10, must be smaller than this section right here. Section right here. And actually, this isn't 7/10, this is also the same 3/10 n, 3/10 n -6. But look what happens is that since we know, let's imagine the array as a single dimension again. So we have basically 3/10 n -6 at each extreme. That the median must be larger than, right? So this value has to appear from here to here. Okay? So we know for a fact that a less than has to be somewhere between, has to be either greater than 10 to the n -6. It has to be greater. The size of this has to be greater than 3/10 n to the -6, or it has to be less than 7/10 n to the +6. Okay? So we are ensured that we're choosing a pivot that doesn't get close to the end of the array. Now, how do we do this in a computationally efficient manner? So to look at that, we go back to our algorithm. Let's go back to our quick select algorithm, okay? So the difference here was that from our previous quick select algorithm is this area here where we choose the pivot. Now we're going to use the median of medians to choose the pivot. And we're going to do that by first breaking A into n/5 5-element arrays. Then we're going to find the median of each of the arrays, of each of the 5-element arrays. And then we are going to find the pivot by calculating the median of the median of the median of the medians, okay? And to do that, we're going to use a recursive function call because this quick select is generalized for finding an integer of any rank, but we know there's a n/5 length array here, and we want to find the median value, which is the value halfway through, which would give us n/10, which is the rank chosen here. And so this recursive function call, this quick select, will give us the median of those medians. Okay, and then we go through the same quick sort, quick select, the quick partitioning as usual. We got the partitioning to find the less than or greater than array. Then if the rank of the pivot is equal to the rank of the element that we were looking to, or return pivot. Else we work on the smaller, we work on one of the, either the smaller value array or the greater value array. So hopefully I've convinced you that's how this works. And because we're using the medians of median 60, this pivot will always be greater than, it will always be somewhere in the center of the array. And so we won't ever run into that territory of of picking a wrong pivot and going to t of n minus 1 or 2. But how well will this algorithm perform? That's the question. And to answer that, let's analyze this array again. Okay. So we breaking the array A into 5-element arrays. That takes constant time, I would say, right? It's just a re-indexing things. Finding the median of each of these arrays. Okay, so finding the median of one of the arrays, finding the median of one of the 5-element arrays takes constant time, but then we got to do it times n over 5 times. Okay, so this takes linear time. Okay, so we got a linear time selection here, which isn't too bad. Now finding this pivot, this quick select, this is a recursive call, right? So it's t of 1/5 n, right there. And this partitioning, again, takes linear time. And finally, we got a recursive call, but a recursive call, again, is that t that depends on the size of the partitions, right? T of max size of a less than or size of a greater than. Okay, so in total, now this, let's before we do the total expression, we know a less than or a greater than because we chose the pivot this way. We know a less than or a greater than has to be less than, comma, a greater than has to be less than or equal to 7/10 n plus 6. That it has to be, right? Because we chose the median of medians, and we're saying that the array a less than has to be either this size, has to be somewhere along this size, okay? And this size is 7/10 n plus 6. And this, because this size right here is 7/10 or is 3/10 n minus 6. So this is just a complement this set. Okay? So we know that this value, t of n, this max function reduces to, because it's a max function, reduces to 7/10 n plus 6, which is approximately equal to t of 7/10 n. Okay, that plus 6 doesn't change things. We're going to leave that alone for now because it'll just make our lives more complicated and it doesn't really change the final output. So the total recurrence for this algorithm is t of n is equal to t of 7/10 n plus t of 1/5 n plus O of n plus O of n plus O of 1. Okay, now these three values here, O of n plus O of n and plus O of 1, what does that become? This still becomes O sub n. Okay, that's the asymptotic bound. So that's good. So we got rid of that kerfuffle stuff. Next, we got t of n, 7/10 n. Oof, I miswrote that. Plus t of 1/5 n times t of n. So we can analyze this using our recursion tree method. Basically, and let's actually switch back to black. N this gets split up into 1/5 n, 7/10 n. Then we go down to 49/100 n and 7/50 n. Then 7/50 n and 1/25 n. Okay, so how much work is done at each level? Well, at the top level is O sub n, right? At the second level, it's 9/10. It is O of 9/10 n. Pretty good, pretty good. And at the third level, it's, let's see, 49 plus 14 plus 14 plus 4, 14 plus 14, 28, 30, 32, 32, yep, 81. 81 over 100 n. Again, we're going down. So the amount of total work at each level is going down. So what does that tell us? That tells us T of n is equal to O sub n. Okay? So the reason this works is that finding the median of each of the 5 element arrays is linear time. Okay, because finding the median of a single 5 element array is just like brute force, constant. You can make like, you only need like, I don't know, let's see, how many if statements do you need in order to be able to find the median? 5 times 4 times 3 times 2. You need like 120 if statements to just find the median through brute force for a 5 element array. That's fine. Then you just do that n over 5 times again. So still linear, it's linear time. Then partitioning takes linear time. And this T of 1/5 n, this finding the median, is less than the benefit you get by choosing a good pivot. And that's the magic sauce. And that is why we chose 5 elements, because basically 7/10 plus 1/5 has to sum less than 1 in order for the recurrence to equal O sub n. That's the magic of it. Let's look at it. Why not? Let's just quickly go through. Why not 3 element subarrays? I'm not going to do 4 element because you don't want to do median with an even number of elements. It just gets tedious. But let's say, why not a 3 element subarray for choosing the pivot? Because then instead of let's just do this out. T of n, this would all be the same, but we would get, what would this value be? So T of n, let's just write the recurrence. And we're going to write it in red. T of n would be equal to, so this would be the range of pivots, right? So if we had a 3 element subarray, we could quickly look at it. And, oh, too loud number, okay. So this will be our median of medians. So then you would be larger than these elements here. And what would that equal? That would be n over 2 times n over 6. That 2 from here times n over 3 times 2 times 1/2. So 2 times n over 6. So it will be 1/3 n. 1/3 n. would be the size of this section here, approximately. So the max of a less than and a greater than would be 2/3 n, right? It's the size of this, correct? So we would get t of 2/3 n plus this this finding the median part, which again, this would now be n over 3 instead of n over 5. So we would do t of 1/3 n plus O sub n sorry, dropped my pen. You can't see that, but I did drop my pen. And so the solution to this recurrence here, if we look at the tree again, n 2/3 n 1/3 n dot 2/3 n 1/3 n 2/9 n 4/9 n 2/9 n 1/9 n. So the work at each level would be n O of n 0 of n. So the solution to this recurrence would be equal to O sub n log n. No better than sorting the entire array and finding itself. So what about larger subarrays? So what about 10 element subarrays? We would get a recurrence that looks like, let's choose another color, T of n, which is equal to T of 13/18 n plus T of 1/9 n plus O of n, which is still equal to O of n. So it does work with larger subarrays, right? However, the issue here is that if you look at the actual tree and how it decays, (13, 18 n 1/9 n). If you look at how the tree decays, you get a decay of O sub n, O sub 15/18 n, O of 15, O of 15/18 squared n, and so on. The decay rate isn't that much better than in the 5 elements, subarray case. So for instance, in this case, 9/10 here is equal to 16.2/18, and here, by using double the size of the subarray, we only get down to 15/18. So the decay rate isn't really that much beneficial, but the brute force work here is so much greater. It's so much greater that it's not worth doing. And so 5 elements is the sort of sweet spot of this algorithm. And that's why we choose 5-element lists. That's why we choose 5-element lists. And so that is a quick select. And it works because this is O sub n, and you use the algorithm itself in a recursive manner to find the median of the array. Okay, hopefully that helps clear up any confusion. I am going to post my scribbles up with, I'm going to attach these scribbles up at the end of my other scribbles and post them up to the course website tonight. Thank you so much for listening, and I will talk to you guys later. Thanks.